All right, welcome back. We're in MECH 1320. We are still working on Chapter 14, but we're going to get into multiple gear drives. So whether we have multiple gears inline or compound gear drives that we're going to deal with. Okay, so we're going to kind of figure it out. We talked about it a little bit in the last lecture, how idler gears really do not affect the system whatsoever. They are there to change the direction of the gear, not impact the overall gear ratio to transmit speed and torque. Okay, so whether it's an idler or a drive with extra shaft, the method to determine the speed and torque is going to be the same. Okay, and we're going to go through multiple examples here. But just remember, idler gears do not affect the torque or the speed in the system. Okay, they cancel out. So we can see that in this example here. All right, we have an input gear or a driver, I cannot speak, sorry guys, a driver gear. All right, that's an input gear that's 30 teeth. We have an output gear that's 60 teeth. And we have two idler gears that are kind of, in between the two here. If we take a look at the ratio, all right, 60/10, then that's the ratio between the big gear and the little gear. Then 10/20, that's the ratio between the two smaller gears. Then we have 20/30. Okay, as you can see, we're going in line. The ratio ends up being 2:1. Okay, it all works out. If you notice in the math shown down below, when we do the simplification, okay, the idler gear actually really has no effect. We can still get 60/30, the output gear over the input gear, and get 2/1. So same ratio. So idler gears do not impact anything. All right, the idler gears in this type of system. All right, so when we have multiple gears attached to multiple shafts, okay, each gear in here is driving a separate shaft that has a separate load on it, okay, and each one has an idler gear associated with it. But I can take a look at the three different output shafts, and I can say I have 30/20. That's one of the output shafts, right, over the input. So it's always output over input. So that ratio is 1.5. I have my middle shaft, which is 10/20, which is 0.5. And I have my last shaft, which is 60/20. When we are in line with the gears, all in line here, okay, we can use the ratios this way. It's going to get a little different. We do our compound differently. But for this, okay, you can understand that it's those three ratios to calculate, whether it's our speed or our torque at each shaft that has an output. All right, then our idler gear has 15 teeth, but that one doesn't matter because idler gears are not affecting our ratio. Okay, so the speed of each output shaft can now be calculated separately using each individual gear ratio that we did in the last slide, whether it's 60/20, 30/20, or 10/20. Okay, the idler gear is not having any effect on the system. Okay, so let's review torque just a little bit. If we want to know input torque, okay, we can take our output torque divided by our ratio. Essentially, we're going to use these ratios here to calculate speed and torque based on our given system. If we want to find total torque of all three of those shafts, all right, we'd be able to add torque 1 plus torque 2 plus torque 3, all right, to get our total torque when we do that. So let's take a look at this system here. We have an input, okay, with 22 teeth, and then we have an output, our driven gear. So we're going to, if we break this down, step by step here, this is just a basic ratio. We're just reviewing ratios, right? 90/22, it's 4.09. So that would be our ratio, and we're going to use that ratio to calculate speed and torque in systems. Now, the two middle gears are our output, or our idler gears. They're not affecting the system. So we can do our output over our inputs. We can do 185 divided by 50 here to get our ratio of 3.7. Okay, so it's very important when we got gears that are in line or stacked like this that we can do this. We don't really care what's going on with those idler gears right now. So that enables us to use the ratio to calculate speed. If we know the output speed or we know the input speed and we know the gear ratio, we're able to do some simple calculations. So here in this example, we're given the output speed as 100 RPMs, and our ratio is 3.7. So we have to know our input speed, okay? So we want to be able to calculate our speed input. So we set it by using the equation given above, okay? So we're going to have speed input over 100 is equal to 3.7. 3.7 is the given ratio. And then we do some simple algebra. We multiply that out, so it ends up being 3.7. We're going to multiply both sides by 100 to get our input speed. And when we do that, we get 370 RPM. Remember, RPM is revolutions per minute. If we want to do the same thing with torque, we can calculate, using all the basic equations that we have now. So input torque, so torque input equals torque output over the ratio. So in this scenario, I give you an output torque of 470 inch-pounds, asking you to find the input torque given a ratio of 3.7. Okay, so if you set everything up correctly, I give you the output, you know the ratio, we can take 470 divided by 3.7. So we get 127.027 inch-pounds. Now, remember, we're either going to be multiplying or dividing by that ratio. It just kind of needs to know if we understand we're going big to small or small to big in that sort of case, okay? So, looking at this problem here, if our output torque is 470, okay, our input torque, is only going to be 127. Don't let the picture be deceptive here. It's just for an answer, because you're like, well, so Lenny, the output gear looks smaller than the input gear, and we know that output gear, since it's smaller, is going to have less torque than the input gear. Don't base it on the picture. Okay, the picture is more for an example of what we're doing. It needs to be based on the numbers. Okay, so don't base it visually on what the picture looks like in this scenario. Base it on the given numbers. All right, and we can use, different ways to get this is still reviewing from the last lecture, okay, but different ways to get the ratio. We can say the output over the input, and N is representing the number of teeth. So in this case, okay, it's 23 divided by 11, which is 2.09, or in the bottom example, we have 40 divided by 11, which is 3.63, okay? So there's how we're going to know our ratio. Now we can use the ratio to get torque, okay? And we can also use our input or output torque to calculate some things. So torque input is torque output divided by the ratio. Total torque is adding all the individual torques together, okay? So we are able to find our input torque, okay, given our output torque. So we have torque output for the first scenario, torque output for the second one, okay? They're both 100 inch-pounds, and we know our output speed for the first one is 2.09. Our output speed for the second one is 3.64. So we're literally going to substitute this into the inputs. We have to find torque input 1, which is going to be just 100 divided by 2.09, right? Our output torque over our output ratio, so we get 47.84. And then for the second one, we're going to get 100 divided by 3.64. We're just pulling the data from the table that's given in the problem. Okay, and then we're going to add these two together to get our total torque. So we're going to take 47.84 plus 27.47, and we end up getting 75.32 inch-pounds of torque. Remember, torque is rotational force. All right, let's take a look at compound gears. All right, these you're going to have to understand more from looking down on top, because this is where we have gears that share the same shaft. So when I start talking about compound gears, all right, we're talking about gears that share the same shaft. So if you look at this picture here, and you notice in the middle there's that dark gray gear, and then there's a smaller gear that's sitting right in front of it. Okay, that's our compound gear because they're sharing the same shaft. Okay, so it's best if we see like an overhead view of these so we can see how those share the same shaft. Okay, now compound gears, our calculations are going to be different. Okay, so two applications that we can have for compound gears are driving two output shafts at different speeds and driving an output shaft that is offset from the driver of the shaft. So that's kind of the two major applications where we use these, okay? So the third application, okay, is we want to do some sort of gear reduction as well. So this compound might be in like a gearbox or things like that. Okay, it's called a reverted gear drive. Okay, but we can use it as our slowing our speed down, all right, because we're increasing our torque in that sort of scenario. So it just kind of depends on the 2 different ways or 3 different ways that we can possibly set these up and use them. All right, so compound gear drive is slightly different, okay? Notice we have speed input divided by speed output, and it's going to be different if we're using speed or torque, so just make sure you understand that. It's going to be our PC. Okay, remember that's our pitch circle diameter of the output divided by the pitch circle input of the input. Okay, times the pitch circle of the compound gear input divided by the pitch circle compound output. So notice when we did our regular inline gears before, it was always output over input. When we use the compound gear is the reciprocal of that. It's input over output. And we multiply both of those ratios. So we have the overall ratio of the input and output gears, output over input. And then we have the ratio of the compound gear, which is the reciprocal. It's input over output. And we're going to do some examples here to help you out. Okay? And just remember, idlers still have no issue or no effect on the system. And now with this, instead of using let me step back a slide. Instead of using our pitch circle diameter, same concept, same equation here, only we're going to use number of teeth on the gear. So N represents number of teeth, else the equation is the same. Okay? So overall efficiency, okay, and this is how you would find it. But let's work through some examples here. Okay? So if we look at the top example here, and we look at the gear ratio, driven to driver, output over input. The output over input is 30 over 10. That's 3 to 1. That's the overall ratio. Then if we look at the compound gear, it's going to be 10 divided by 20. So that ratio is 1 to 2. So our compound gear ratio, we can get by multiplying these together. 3 over 1 times 1 over 2, okay, gives us 3 over 2, which is a 3 to 2 gear ratio. Okay, we can also do it the other way, right? The ratio is input speed over output speed. So we have 1800 divided by our output speed, and that equals our 3 to 2 ratio. So our output speed is going to be 1200. So we'd take 1800 divided by 3 over 2. Okay, when you do 1800 divided by 3 over 2, you're actually going to multiply by the reciprocal because it's a fraction. So you're going to take 1800 times 2 divided by 3 in this case, all right? So you got 3600 divided by 3, or yes, divided by 3, sorry, which gives us the 1200 there. Okay, so there's how we're working with a compound gear drive using ratios and speed. Okay, I'll let you pause and write down for torque. Instead of, if we take a step back here, remember speed was input speed over output speed times the ratio. When we look at torque, it's output over input. So torque is the reciprocal of speed, right? And that makes sense because they're inverses. Remember, in a system, if torque goes up, speed goes down and vice versa. So make sure you write down these equations here, and we're going to roll through them in an example. So you might have to pause and go back. All right, so given the following input, all right, our input speed is 3,500 RPM. Our output number of teeth is 35. Our input number of teeth is 16. Our input for our compound gear is 42. Our output for our compound gear is 29. And you can study and see where those are on the given diagram on the right-hand side. So we're just going to find the driven shaft speed. Okay, the driven. So what is that? That's the output speed. The output speed is the driven speed. Okay, so I'm just going to substitute all of our given data into the equation above. Okay, so you can see as such. Then we're going to take that ratio, that 35 over 16 times 42 over 29. And we're going to get our value there. So our ratio ends up being 3.1681. Okay, and then since I need to find output speed, I'm going to multiply both sides by output speed and then divide both sides by the ratio. So when I do that and set that up algebraically, I end up with 3,500 divided by 3.1681, and that's going to give me my output speed. And when I do that calculation, my output speed ends up being roughly 1,104 revolutions per minute. Okay, let's do another example here with torque. Okay, same concept. Okay, you're gonna need to know and understand the equation, but we're literally just gonna substitute in given values. And this is how it'll be on the test too. I'll give you a scenario. You need to substitute in the given values. Okay, the most important piece you got to understand is this is a compound gear drive. So remember, when we use compound and we use the compound gear, it's input over output instead of output over input. Okay, so the overall is always output over input. The compound piece is input over output when we do that. So just make sure that you're paying attention that it has to be the reciprocal when you do a compound gear drive. All right, but we want to find the output torque. Okay, the driven shaft is the output torque. So we're going to substitute everything that we have that's given. Okay, same ratio as the last example, so we don't have to really do any new calculations there. And in this case, to get the output torque, we're going to take our ratio, which is 3.1681, and multiply it by 360. So our output torque is going to be 1140.52 inch-pounds. Okay, remember, torque's a force, so our units are going to be inch-pounds when we do that. All right, so let's find the driver's shaft speed. So that should be our input speed. All right, once again, you're going to find that these are, relatively the same. Once you understand the equations that you need to know on a test, it's really just substituting in our given values. Okay, so in this case, make sure we're paying attention to the ratio. The overall ratio is 53/48. The input, or the compound gear ratio, is 91/197. That's the part that's going to throw you off. Remember, it's a compound gear, so we got to use that reciprocal on the compound gear ratio. So when we do that, we have our input speed divided by 6372. That's our given output RPM, times our ratio, which is approximately 0.51. And then we multiply both sides by 6372 to get our input speed. So you're going to take 0.51 times 63.72 and get 3250 RPM. Okay, 3250 RPM. So the compound gear does affect the overall ratio and does affect the overall speed when we do these calculations. Let's do an example. Same stuff with torque here, only this time we're doing the driver, right? So the input torque for this. So substitute in all your given values. Same ratio as the last slide for simplicity. So our ratio is 0.51. And then we have to multiply both sides by the input torque and divide both sides by the ratio. When we do the algebra step, it ends up being 383 divided by 0.51. All right, so our input torque is going to be 750.91 inch-pounds. Okay, we're going to run through a couple more examples here and then we'll be done. But what is the driver shaft's speed? What's the difference in this problem versus the last two? Notice that there are two sets of compound gears instead of one. So you must include them in the ratio. So this system has more compound gears. Everything else, the setup is the same. And the ratio doesn't change for compounds. Compound will still be input over output, but in this case we have two separate compounds. Okay, so we're going to have to make sure that we include both compounds when we do this calculation. So really, we're just taking the last two examples to the next level by throwing one more compound gear. And remember, this one applies to like the third method for compound gears that we talked about earlier. Okay, so in this case, you need to recognize the system, because on a test I would give you, a picture like this, and you would have to be able to calculate everything correctly for me and show me by substituting in the given values and making sure your ratio is correct. It should be 22/11. That's the overall ratio. The first compound gear is going to be input over output, so 21/26. And then the next one's going to be 21 divided by 20. So we got to be careful, make sure we're pointing and picking out the right teeth when we do that. So when we do this, our input speed, okay, is going to be 2043, which is the output speed, times our ratio, 1.696. And when we do that, okay, our input speed ends up being 3,465 revolutions per minute when we do this. All right, and then we'll do one more example of this. Same kind of setup with multiple compound gears here with torque. All right, same scenario, same number of teeth, same ratio. I don't want to complicate things for you here, but this time we're using torque instead of speed. So substitute in what you have, 388 divided by our input torque times our ratios. Okay, same ratios as last slide, so they're 1.696. So our input torque here ends up being 388 divided by 1.96. Okay, we have to multiply both sides by input torque, divide both sides by the ratio to get our input torque. So when we do that calculation, our input torque ends up being 228.7 inch-pounds. Okay, so this wraps up chapter 14, where we've talked about multiple gears now and doing the calculations, and we've talked about doing a compound gear drive. You are going to have a lab, all right, where you build both. You're going to have an inline and you're going to have a compound gear drive. The compound gear drive is where you're going to learn to mount the variable speed motor in this scenario as well. So once again, guys, this wraps up gears. If you have any questions, feel free to email me or ask me in class. Else, guys, we'll get the labs done on this, the homework calculations, and have a great day. I'll see you in class.